Okay, thank you for giving us much time to work on this project. And when we look at this project, it's about analog system analysis and discrete system analysis and the difference between these two. When we come to the first one, to analog system analysis, there are 5 graphs. And the first graph is about pole zero plot. The second one is impulse response. The third is frequency response. The fourth is phase response. And lastly, and fifth is time domain input-output comparison. When we look at each of them individually, the first one, the pole zero plot, it shows the system poles, like 1 or 2 poles in the left half of the S-plane. This indicates a stable, low-pass system since poles are far left on the real axis, which means there are no imaginary part suggests or no resonance or oscillations. And when you come to the second one, the impulse response of h of t, it shows that it decays exponentially, confirming a stable system, and it matches expectations from pole locations, which means from real poles exponentially decay. And when you come to the third one, it shows that a frequency response, which is h of j omega, shows that magnitude plot shows a low pass characteristics with a gradual roll off, and it cuts off frequency appear around 200 and 400 Hz. And we come to the fourth one, it shows that it's a phase response angle h of omega, and it shows that a phase decreases gradually with frequency, typical for real pole low pass filters. And the last one, which is time domain input output comparison, shows that two inputs x1 and x of 2 are shown with their corresponding outputs y1 and y2. Outputs are compared with Fourier series for periodic like inputs and analytical convolution for arbitrary inputs. This verifies the system's linear time invariant behavior in continuous time. Well, this is all about analog system analysis. And when you come to discrete system analysis, also there are 5 graphs in discrete system analysis. The first one is pole zero plot on the z plane. The second one is impulse response h of n. Third one is sampled input and discrete outputs. And the fourth one is digital frequency response h of omega. And the fifth one is digital phase response, also h of omega. When we come to the first one, which means pole zero plot on the z plane, shows that poles are inside the unit circle, which is stable discrete system, and poles are real and positive, which means impulse response will be decaying without oscillation. It's likely obtained with impulse invariance or a similar mapping from S plane to Z plane. And we come to the second one, which is impulse response h of n. It shows that a sampled version of h of t, which is decaying exponentially, and it's labeled from impulse invariance, which confirms the design method. And when you come to the third one, it is sampled inputs and discrete outputs, which is x of 1 and x of 2n. They are sampled versions of the continuous inputs, and their outputs y1 and y2 are computed with discrete convolution. When we look at this, they match the sampled analog outputs, which is validating the discrete system model. And the fourth one, digital frequency response h of omega, it shows that magnitude response is periodic. It's likely due to sampling, and it shows that low pass shape similar to analog, but it is repeated at multiple of sampling frequency, and it shows some aliasing effects at higher frequencies. And the last one, which is digital phase response of h of omega, this shows that phase is roughly linear in the passband but wrapped periodically, and is comparable to analog phase but with periodic repetitions. When we look at the key comparison of these two systems, the analog system analysis and discrete system analysis, the key aspects are stability, impulse response, frequency response, design method, and input-output validation. When you compare these two, on stability, the analog system poles in left half S-plane are stable, and on discrete system, poles inside unit circles are stable. And when you look at the impulse response of these two, on analog system it's continuous decay, and on discrete is sample decay. It matches analog at sample times. And when you come to frequency response, on analog system it's low pass and smooth roll off, and on discrete system it's low pass, periodic, and summarizing. And we look at the design method. Analog system, natural continuous time design, and on discrete system is derived via impulse invariance. And when you look at the input and output validation, on analog system, Fourier series and convolution method. It's used Fourier series and convolution method. And on discrete system, it's used with discrete convolution match sampled analog output. These are the key difference between these two. Well, when we summarize all these two comparisons, which is analog system analysis and discrete system analysis, it gives us information on how to convert analog to filter, how to convert an analog filter to a digital one using impulse variance. And the other thing is how a system properties like stability, frequency response are preserved or altered in the discrete domain. And lastly, it shows us that how time domain convolution and frequency domain analysis align in both continuous and discrete cases. This is what we have for our presentation. Thank you.